We're going to compute a determinant of a 3 by 3 matrix using what's called a cofactor expansion. And I'll show you how to do this in the solution, okay, and introduce a little bit of notation to you that you'll see in the book. So let me give you a moment to copy this example down. For a determinant of a 3 by 3. But in linear algebra, we want a method that's going to work for determinants of 3 by 3s and 4 by 4 matrices, any size matrix, 5 by 5 matrix. We really need a procedure that's going to work. So we're going to use what's called cofactor expansion. And let me go to the next page here and show you how I'll show you how this works. First of all, with cofactor expansion, you can expand along any row or any column to compute the determinant of a matrix. Okay, so to compute the determinant, we can use cofactor expansion along any row or column we wish. Okay. So the natural thing is to use cofactor expansion along the first row. You know, naturally, if we're going to do a cofactor expansion to compute a determinant, and we can pick any row or any column, I think most people on their first try would pick the first row. Okay, and all right, so let me give you a moment to, copy this down up to here, and then I'll talk about it, okay? Be easiest that way, I think. All right. Okay, so let me show you what we're doing here. So, okay, we're going to do a cofactor expansion along the first row. So what I do is I block off the first row of the matrix. Now, there are 3 numbers in the first row. Those are the A numbers. So for instance, the number 1 is A11. Okay. The number that's A11. The number 5 here is A12. That's the number in the first row, second column. The 0 here, oh, that's in the first row, third column. That's A13. Okay, so there are 3 parts to computing this determinant. The next thing we do is in each, if you notice in each part here, we're multiplying by -1 to some power. So here we have -1 to the 1 plus 1 power. Oh, well that, A sub 1, 1 plus 1 power. Over here, we have -1 raised to the 1 plus 2 power. Oh, okay, A sub 1, 2. First row, second column. And then over here, we have -1 raised to the 1 plus 3 power. Oh, okay, A sub 1, 3. First row, third column, 1 plus 3 power. Okay, so I'm trying this, I think it's easiest to see how this works sort of by doing it piece by piece. The final thing left are the I want to say this the right way. One moment. I'm going to hold on. One moment, class. So we have those little determinants of the submatrices. Okay, so the first, let me just see here. I want to make sure I'm using the right terminology here. One moment here. Yeah, that's right. Submatrix. Okay, so oh, okay. So how do we get this submatrix here? How do we get that? Well, what we do is since that submatrix goes with the A sub 1, 1, okay, the 1 there, the 1 is in the first row in the first column. So if we block off the first row in the first column, that's going to give us, for the submatrix that's not blocked off, is 4, -1, -2, 0. Okay, so let me actually show you this again here. Let me show you this again. So number 1, the 1 in the top left-hand corner of the matrix is in the first row and the first column. So the submatrix then that's left is 4, -1, -2, 0. That's this matrix here. Are there any questions on that? Please let me know if you're uncomfortable. All right, let's look at the second submatrix here. So the number 5. 5, okay, is in the second row, first column. Sorry, it's in the second column in the first row. So the submatrix that results consists of 2, 0 and negative 1, 0. That's right here. That's right there. So far, who's feeling good? Who's feeling good so far? Okay, Abby's comfortable, Eleanor's comfortable, Hung's comfortable. Good, good, good. Okay, let's do the last one here. The last part of the determinant, the 0. The 0 is located in the first row and the third column. So the submatrix that's left is a submatrix with 2, 4, and 0, negative 2. And that's what we have here. Okay. Are there any questions? Any questions at all on what I just showed you here? All right. All right. Well, a little bit more now, a little bit more. So when we expand along the first row to compute the determinant, the formula says take the element in the first row and multiply it by its cofactor. This whole thing is the cofactor C11. And then you take, you know, you take the element A sub 1, 2. That's equal to 5. And you multiply that by the cofactor given here, C sub 1, 2. And then you take the element 0. That's the element in the first row, third column. You multiply that by the cofactor C sub 1, 3. Okay, C sub 1, 3. And when you expand it out, all this out, you'll get a negative 2. So of course, the this here is the determinant for that first submatrix. This here is the determinant for the second submatrix. And then the third part of the determinant, oh, I just put a 0 there because I'm multiplying by, you know, 0 is a product in the product. So, you know, but in any case, you get negative 2. Are there any questions at all? Okay. Well, let me bring up the ebook for a moment. Let me bring up the ebook for a moment. Does everybody have this copied okay? May I move to the ebook? All right, very good, very good. Well, let me move to the ebook. Very good, very good. And I can, so in the ebook here, okay, this theorem 1 is the theorem that that I just showed you. Well, this is a general statement of the theorem for computing the determinant of a matrix, but you see where the determinant is simply it's a linear combination of of the cofactors, where every weight on the cofactor goes with it depends on what row or column you're expanding on. Okay, but they give this theorem, and and incidentally, the plus or minus signs, okay, that are part of the cofactors. There's a little thing that I find very helpful. Every little cofactor has a -1 to the I plus -1 to the power I plus j. But that is just equivalent to having a matrix where, like, the number in the top left-hand corner is going to have a plus in front of it. The number below that would have a negative in front of it. The number to the right of that would have a negative in front of it. And it just kind of branches out like that with the pluses and minuses. How many find that picture kind of helpful, that little diagram there? I find it helpful. I hear you, Lewis. I hear you. I'll tell you what, let's go back to the example. Where we're finding the determinant here. And can you pick we expanded along the first row. We got the determinant of the matrix A equal to -2. But we can expand along with cofactor expansion, we can expand along any row or column we wish. So what might be, let's pick a column. Let's pick a column. Let me ask you, what column in this matrix A, what column would be the easiest column to expand along? The first column, second column, or third column? What would be the easiest column to do cofactor expansion along? The first column, the second column, or the third column? Which would be easiest to use for cofactor expansion? Benjamin, you said the third. Shravani agrees, the third. Why? Why is the third the easiest one to use? Good, Hung, because of the zeros, and I'm sure Benjamin and Shravani agree. That's right. Well, I don't want to make it too easy here, so I'm going to expand along the second column. Okay, so here would be cofactor expansion along the second column. Okay, let me give you a moment. So I'm just applying the algorithm as I did when I did cofactor expansion along the first row. Let me give you a moment to copy, everything down up to here, and then I'll go over this with you. Okay, so I'm going to use the second column. I'm going to use the second column here. So, of course, the second column has a 5, a 4, and a -2 in it. And then the -1 to the powers would be defined as you see here. Are there any questions on that? Okay. Well, then we have to worry about the submatrices in the cofactor expansions. So for the submatrices, of course, we're going to be expanding down the second row. So for the 5, okay, the first part of the determinant, I'm going to block out the second row. The 5 is in the second column and in the first row. And so this is going to be then, my corresponding submatrix will consist of 2, 0 and -1, 0. And that's what's right here. How many find this? Is this writing on the page helpful? How many find that helpful? Just want to kind of doing a little survey. Okay, good, Abby. Thank you. Good, Hung. Wonderful. Good, Olivia. All right. Thank you, Catherine. All right. Very good. Very good. See, when I have the examples prepared like this, I can do this. I can do the drawing. So I'm glad you find it helpful. All right. Let's continue here. All right. Now let's worry about the second part. The second part of the cofactor expansion, where the 4 is. Well, the 4 is in the second column and the second row. And so then the submatrix should consist of 1, 0 and 0, 0. And it does. See? And this is in the recording, of course. Okay, and then finally, the last part of the determinant, okay, the third part has a -2, the -2. Well, -2 is in the third row and the second column. And so you see here then the submatrix that's left over would consist of 1, 2, and 0, -1, and it does. And if you compute then the determinant, you're going to get a -2. You will get a -2. As you should. I mean, any row or column you expand along, any cofactor expansion you do along any row or column is going to give you the same answer. Okay, are there any questions on this? All right, well, let me go back to the book. I want to look at example 3 in the book then. you're good with this, I'll move to example 3. Okay, let me do that. Hold on here. I actually could have left that up, but it's fine. Okay, so let's go down here. Look at example 3. My goodness. A 5 by 5 matrix. All right, we need to pick carefully here. We need to pick carefully. We need to pick carefully which row or column that we're going to expand along. Well, what would be your, what would be good choices here for expanding along? Like, what column would be the best column to expand on for a cofactor expansion? What do you think? Eleni, good. And why do you like the first column, Eleni? Lots of zeros. Good, good. All right, well, what about in terms of a row? Is there one row that's better than any other row to expand along in this matrix for a cofactor expansion? Good, Catherine, 5th row. Because again, a lot of zeros there. So, and this is something that, you have to do. You have to realize it before you do the cofactor expansion, right? On an exam, for instance, a timed exam, you don't want to pick the you want to pick the easiest row or the easiest column, right, to compute your determinant on. All right, and I like to see all the work and the steps. Okay, let me see here, one moment. So the book says, okay, the book says expand down the first column of the matrix A. And if you do so, whoops, this is going to be your result here. Now I want you to look at that and make sure you're comfortable with that. Please. In other words, what I'm saying is this step right here, okay, let me take this off. Are you comfortable with what you are seeing there? Are there any questions at all? Okay. Benjamin and Laney are comfortable. Do you see if you hold on here. For the 3 in the top left-hand corner, if you block out then the first column and the first row, the 4x4 matrix that isn't highlighted in yellow is what you see down here at the bottom. Whoops, hold on. Hold on, one moment. Let me. Okay, so it should, and bring it back up. Okay, so once again, the matrix A, if I highlight the first row in the first column, the 4x4 matrix that's not highlighted is what you see down below here when they compute the determinant of A. Okay, and so, okay, and I don't know what that was. I don't know what that was. Oh, I know what that was. All right, hang on, I'll get rid of that. All right, no problem. So, okay, well now we have this 4x4 matrix. Which row or column do you want to expand on? I mean, if you had to pick a choice, what would be your choice here? So we haven't computed the determinant. Yeah, I don't know why it keeps doing that. You have to forgive me, class. Hold on. I don't know why it keeps. Can you? Unbelievable. Hold on. This is something I'm gonna have to get fixed. Hold on. I mean, we're doing okay, but I'm not gonna have this, you know, happen here as a general rule. So I'm gonna. Okay. So tell me that 4x4 matrix at the bottom there, what column should we expand on? The first, second, third, or fourth? The first column. All right, good, Nafani. Absolutely. And so that's what we'll do. So if we do that, then if we do that, this is going to be the result. Okay, and you know, it's really you learn by doing. You learn by doing. And what I want to do is I want to give you a little class time to work on this section 3.1. They note in theorem 2 that if you have a triangular matrix, the determinant of A will be the product of the entries on the main diagonal. But again, to intuitively feel comfortable with that, you have to do a little practice. But I want to ask you a question here. Now, we're working with 3x3 matrices, finding the determinant of a 3x3. We're finding the determinant of a 5x5 matrix. We just looked at that. Hold on here. And my question is, you know, this cofactor expansion approach. Can you? I mean, we you know, it works okay for 3x3, a 4x4, 5x5. We're able to manage it, you know. But do you think it would get labor intensive if we had larger matrices like a 10x10 matrix, If we were to do cofactor expansion for a 10 by 10 matrix or a 20 by 20 matrix, and let's say there weren't a lot of zeros in the matrix, maybe it was what's called a dense matrix. Can you imagine that this cofactor expansion process would be somewhat cumbersome? Yeah, it would. It would. And so take a guess if you had, let me just see here. All right, so hold on, class. Sorry, I had a, so take a guess how long it would take to compute a 25 by 25, how long would it take to compute the determinant of a 25 by 25 matrix? In other words, a matrix with 25 rows, 25 columns. If you were to use actually a computer that could perform 1 trillion multiplications per second, how long would the computer have to run to compute that determinant for a 25 by 25 matrix? How long do you think the computer would need to run? Maybe your computer at home, for instance. Okay, if we're going to use this cofactor expansion approach to compute the determinant of a 25 by 25 matrix, okay, 25 rows, 25 columns, how long do you think it would take your computer to do it? Let's have some guesses here. Okay, Shravani says around a second. Okay, I'll bring up the, hold on here. 2 minutes, okay, Catherine says 2 minutes. Half a second, Hong says, okay. All right, do we have any other, okay, 1.345 seconds. Okay. Right, well, Justin, run or to process. All right. Well, you know, all of you have made your guesses are good, but it would actually take 500,000 years to compute a determinant for a matrix that's 25 by 25 rows, 25 columns, using cofactor expansion. Yeah, I'll show you here. I know, you don't believe me, right? You don't believe me. All right, hang on. Let me show you here. Look at the numerical note right here. Okay. See that? If a computer performs 1 trillion multiplications per second, it would have to run more than 500,000 years to compute a 25 by 25 determinant by this method. What do you think of that, class? How many think that's absolutely amazing? Yeah, yeah. I was surprised too, and saying it is great. And you know, they're talking about the cofactor expansion there. It requires more than n factorial multiplications. 25 factorial is approximately 1.5 times 10 to the 25th. How many remember factorials grow quickly? Like, you know, a factorial will grow quickly. Like, yeah, it grows quickly. You know, like 3 factorial is 1 times 2 times 3. 4 factorial is 1 times 2 times 3 times 4. 5 factorial is 1 times 3 times 4 times 5, and so forth. So, yeah, so clearly cofactor expansion is, I mean, we need to use it, but we can't, we have to have a faster method to help us. So to help us, we're going to learn what are called properties of determinants in section 3.2. That's what we're going to use to help us so that it doesn't take 500,000 years to compute a 25 by 25 determinant. And on that note, let me stop the recording. I want to give you a little time to work on section 3.1, about 13 minutes here. And then I'm gonna, the last 5 minutes of class, let me stop the recording here.